Okay, the second part of section 5.7 is actually just example 5.4, and we'll work through this together. And this is on page 104 in our textbook. It says that I have a shunt motor. How do I know? I know it's a shunt motor because I see this field over here that's in parallel with the armature. The line current is 51 amps, and the shunt field resistance is 120 ohms. So any voltage I see across here, I'll also see across here, right? Because they're in parallel. If the armature resistance is 0.1 ohm, and normally those resistances will be very small, he says, I want to know the current in the armature. I also want to know the counter EMF, and I also want to know the mechanical power developed by a motor. Now, when you first read something like that, I mean, that's a little overwhelming. And so what you've got to have is you got to have these equations in front of you. You know, what matches up with what the question is. So, you know, I guess maybe the first thing too I could look at is to maybe figure up some other things that are given. So you know, I've had these circuit analysis classes, and I know that if this 120 ohms here, right, this 120 ohms that is here, it's in parallel with a 120 volt source. I'm basically saying 120 volts divided by 120 ohms, and that gives me 1 amp of current that would be down the field here, which we'll call our excitation, and it's 1 amp. Now, just goes to reason that if this is 51 amps here, right? This is 51 amps here, then if 1 amp is here, then there must be 50 amps traveling through here. Okay, so first off, let's say that we have the field current equals I sub x, and that is 1 amp. The armature current is 50 amps. Okay, so we'll call that what? I sub A. 50 amps equals I sub A. And then we've answered actually the first question, haven't we? So we've got 50 amps in this circuit. All right. The next question here is, what is the counter EMF? Okay, so the voltage across the armature is 120 volts, right? Now, I do believe we have an equation that is going to help us with this. We don't even need an equation yet, though, excuse me. The voltage across the armature is 120 volts. The voltage drop due to this armature resistance is going to be, since there's 50 amps coming through here, right? We've already determined that from here. Then 50 amps times 0.1 ohms will give us a voltage drop of 5 volts across here. Okay, here's all our numbers so we know so far. 1 amp for excitation, 50 amps through the armature, 51 amps total. All right, so far so good. The CEMF generated by the armature, E sub O, is going to be, what is the voltage across here? Well, from top to bottom, it's 120 volts. I dropped 5 volts here, right? Minus 5 here. So that leaves 115 volts here. So E sub O has to be 115 volts. See, we knew so much. We knew a lot more than we thought we knew, right? Even getting started with this. So what is the total power that is supplied to the motor? Okay, so think all the way out here, think all the way out at the source, right? And what is the total power that's being supplied to this motor? Okay, well, it's 120 volts and it's 51 amps, 120 volts times 51 amps. And what I get with that is 6,120 watts power being supplied to the motor. How much of that power that's being supplied is actually absorbed by the armature? How much of that is actually absorbed by the armature? Well, that's a little different calculation, isn't it? But We know that the power absorbed by the armature will be the current times the voltage across the armature. And remember that this is a part of the armature. So this is 120 volts times 50 amps, and that is going to be 6,000 watts. Okay, so we answered the question. We're getting there. The power dissipated in the armature, power is going to be the current squared times the resistance. Oops, there's a mistake in your textbook. Look on the bottom of page 104. It has this new thing here, IR squared. We don't know much about that, right? That's just a typo. That should not be there. What you should have is I squared R there. Make that correction in your textbook. So what is that going to be? Well, that would be 50 amps squared times a resistance of 0.1, which gives us 250 watts of power that are dissipated in the armature from the resistance there. Okay, now the mechanical power developed by the armature is, it's that EO term. The power is equal to EO times the current. Okay, and so we could calculate it out that way, or since we already know it's 6,000 watts here, that's what's supplied, and we lose 250 watts there, then we could get there that way, and it would just be 6,000 minus 250, and we would come up with 5750 watts, which he tells us 5750 watts divided by 746 would give us this answer in horsepower, which is about 7.7 horsepower that we'd be looking at for this problem. And wrapping this up, if we go back, and I just want to point this out right quick, we could have gotten to the same answer two different ways, but equation 5.4 said that the power at the armature is equal to ultimately this, and this is the power dissipated in the resistance, right? And so that was this number here, and I could run that into the calculator, and I could come up with that number. Let's see if that works out. If the current squared, 50 squared times 0.1, sorry for the mess, 50 squared times 0.1, 50 squared times 0.1, I get 250 watts from there, okay? So I could have used equation 5.4 to get there. And he also told us in the text that this term was actually the electric power that's converted into mechanical power, okay? And we could have gotten there the same way. The E sub O, the armature voltage, is 115 volts, and the current is 50 amps. And if I multiply 115 times 50, I get 5,750 watts, which of course matches up to here. So we could have gone at that either way. And I think you'll see this as long, you had that same sort of situation like in circuit analysis and other things. There's more than one way to get there. And, depending on what's easier, I guess we thought, hey, we've already done this here. It's just easier to answer those questions from those calculations. All right, 5.7 is done. It's quiz time. This is a good time to catch up with everything and knock out those two quizzes. And then I will hunker down here and try to finish this chapter up for you. We've actually done the hard work in this chapter. The rest of it is much more qualitative in the sense that, you know, most of the heavier calculations and so forth are done. The understanding of the workings of this motor are done. And now we'll just finish this up with some enhancements. Okay.